Interference of sound waves. You can see that the interference alternates between loud spots and spots of no sound. Just as we stated before, if we draw that yellow line, and we'll draw that yellow line along this reference line, and we were to walk along that yellow line, that's in proximity to two speakers that are creating identical sound. We're going to hear loud, soft, loud, soft, loud, and so on. This is an interference pattern or an interference fringe that occurs. And we hear loud and soft, or loud spots and no sound, depending on where we stand, because the sound waves are traveling various distances. When we're standing at this central loud spot, this means the sound has traveled equal distances. And when the sound reaches that point, the sound waves are in phase and we hear loud. At this location, we hear no sound. That means when the waves reach, they are out of phase. At this location, they're off by 1/2 of a wavelength. At this next location, they're off by 2 wavelengths. Or excuse me, 1 wavelength. 1.5, and then finally 2. Interference of sound waves. A constructive interference pattern is given by the equation d sine theta equals m lambda. For small angles, the sine of theta is equivalent to the tangent of theta. So the x location of the fringe, I'll tell you what that is in a moment, divided by the length, which is going to be the sine or the tangent when we use small angles, is approximately equal to, or is approximated by, the m value, the order, times the wavelength. So if we were to come up and, first of all, let's duplicate this slide. So we'll clone it so it's available again for consideration. If I were to draw a triangle, and I'll do that with yellow lines for my first triangle, and we call that angle theta. I'll just color it there. That's the angle theta. This is the opposite side, and this is the hypotenuse. So we should draw in this case. Again, this is the opposite, and this is the hypotenuse. Let's consider a different triangle at a lesser angle. And I'm going to draw this one with, we'll draw it with pink. It may be hard to, let's pick a different color. We'll use this green. If I consider this triangle, which is a much smaller angle, again we have an opposite and a hypotenuse. But in the case of the triangle, the hypotenuse, where the angle is very small, will approximate the size of the adjacent. So the opposite, sorry about that, the hypotenuse and the adjacent are labeled out. And where the hypotenuse and the adjacent are about the same size, instead of using sine of theta, which is opposite over hypotenuse, we can use tangent, which is the opposite of the adjacent. This opposite side we'll call x, and the adjacent side we'll call the distance we are away from the speakers, L. Small angle approximation explained. Alright, in this slide we're going to explain the value for orders and what they mean, or the M value. So again, we'll just state the value for M is called the order, and M also corresponds with the number of wavelengths that we're off by. If we're at this loud spot, it's associated with M equals 0. That means sound travels from the top speaker to that location and the bottom speaker. And since they're the same distance away, that location would correspond with crest meeting crest or trough meeting troughs. We'd have constructive interference. And in that case, because the waves are in phase and they've traveled the same exact distances, we'd be off by 0 wavelengths. So when M equals 0, we're off by 0 wavelengths. And that only occurs one time at the central fringe. When we come up to this next spot, M equals 1, above, or at some X location away from that central fringe, at that location, waves would travel from speaker A and speaker B. Since it's a loud spot, they're said to be in phase. However, at that location, where M equals 1, we're off by 1 complete wavelength. Next above, this next loud spot, M equals 2, again waves travel from speaker A up top, as well as speaker B from the bottom, and they travel farther from speaker B, the bottom speaker, and they would travel a difference in distances that corresponds with 2 wavelengths. So for M equals 2, we're off by a total of 2 wavelengths. So the order is the location associated with the location, and it also corresponds with the number of wavelength differences that the sound waves travel between these speakers. And this is beautiful. Here's another beautiful thing. We have a 0th fringe right in the center, but there's symmetry about the locations. You'll have a first order fringe some distance above the loud spot, or the central fringe, as well as below. So if M equals 1 is, 10 centimeters above the 0th fringe, you'd have another constructive interference that is associated with them being off by 1 wavelength, that same distance below. And again, we have 2 and 2. If there were a 3 above here, there would be a 3 below also. Symmetry is a beautiful thing. A destructive interference pattern is given by an equation d sine theta is equal to m plus 1/2 times lambda, where again d is the distance between the speakers. The angle theta refers to the angle that's formed between these dashed lines in the x-axis in this case, or this horizontal line. M is the order, and lambda is the wavelength of the sound. For small angles, and we're not going to explain the small angle approximation again, sine of theta is approximated by tangent of theta. So the sine of theta would be dx over L, where the tangent of theta would be dx, x location, divided by L. All right, now that we've explained the small angle approximation, let's talk about the physical meaning of the orders, not for constructive, blue locations, loud, but the green locations, which are no sound or soft. So again, a destructive interference pattern is given by d sine theta equals m plus 1/2 lambda, where m is the order of the interference fringe, and x is the location or the spot where no sound is heard. So we're going to apply this formula, m plus 1/2, and it's going to tell us how many wavelengths we'll be off by when we're standing at these locations. So in the first case, let's use m equals 0. A destructive interference pattern is given by the equation d sine theta equals m plus 1/2 lambda. And we want to remember that m is called the order of the interference fringe and is the x location where no sound is heard. So if we're at that location, there's no sound, that's m equals 0. If we're just below, an equal distance away from that central fringe, a loud spot, again, it's m equals 0. Up here and down, it's m equals 1. In these cases, all 4 cases, we're going to observe destructive interference when we're standing at these locations. So what does the m plus 1/2 signify? It does have a special meaning. It turns out that it's the number of wavelengths that you're off by when you're standing at these various locations. Here and here, let's just say the black dots, I'll put a dot here, they're the 0th fringe. If we put red dots here and here, that's the first fringe. So in the 0th fringe, that m plus 1/2 is the number of wavelengths you're off by. So where m equals 0, and if we apply m plus 1/2 lambda, we'll put a 0 in where m was, and 0 plus 1/2 is, it's interesting, 1/2 of a wavelength. So at that location, we're off by 1/2 of a wavelength. And down here, we're also off by 1/2 of a wavelength. So if we're standing at those 2 black dots, that means sound will travel 1/2 wavelength greater distance from one speaker than it did the other. So if we're at the top black dot, m equals 0, that means the distance from speaker A to that dot is 1/2 wavelength smaller than the distance from speaker B to that same dot. If we're standing at the bottom, m equals 0, we're still off by 1/2 wavelength. But it means the distance from speaker B to that dot is 1/2 wavelength smaller than the distance from speaker A to that spot. Let's apply this to the other fringe, and we'll just use colors. M equals 0 corresponds with these 2 dots. Well, we made a mistake. That's not m equals 0. Again, that's m equals 1. So I'll write the equation, m plus 1/2 times lambda, so we're looking at the right side of that equation. And we'll say that m equals 1 here. We're just going to use a different color to contrast. Well, I'll use purple. M equals 1 is the next fringe. 1 plus 1/2 happens to be, and I'll just rewrite, 1 plus 1/2 is 3/2 of a wavelength. So at this location, we're not off by 1/2 of a wavelength, we're off by 3/2 of a wavelength. And down here would be 3/2 of a wavelength. Can you guess what the next fringe would be? That's right, you're going to be off by 5/2 of a wavelength, an even greater number of wavelengths that you're off by, or the difference in paths. So we can predict how many wavelengths we're off by, or they differ by using the order. The most common mistake is that, hey, with constructive, we know that this is m equals 0, 1, 2. We don't start off in the first order. We start off on the 0th order, and that makes it so when you use the equation, they're off by 1/2 of a wavelength. Nice work.